periodic sclerosis on stress strain behavior in osmotic fracture parts with SLM.
Thank you, and good evening. I will try to do the presentation a bit longer to avoid the questions at the end. This research has to do with the examination of the material itself. What we have done is we're trying to fill in a gap in the literature, first of all. It has been identified by a few researchers over the past, say, 12 months, 18 months roughly, that there is a gap within the literature in the low cycle fatigue behavior of metal additive manufacturing. There have been a lot of studies on the monotonic behavior of these materials, but also studies around the high cycle fatigue behavior, but very few published data exist, at least in the scientific literature, things that we can actually access as researchers that can help us understand how these materials, especially the ones which are currently used in biomedical applications and aerospace applications, how they behave under low cycle within the low cycle fatigue regime. So this is a preliminary investigation we did. We selected titanium 64 because it's a metal which is widely used today by researchers and by the industry. And the objective is to extend this area. So this research has been conducted at RMIT University in Australia, in particular in the Center of Additive Manufacturing. So the machine we have used is an SLM 250, SLM Solutions 250 machine. The processing parameters are the typical ones, the typical ones which are used in most of the work that RMIT is doing in conjunction with industry. So there are projects that RMIT is working on, and these are the typical parameters. We have done some previous studies with some slightly different parameters, but our objective, of course, was not to optimize the parameters, but rather to identify the material behavior under typical parameters. What we did is we got some samples out of the SLM machine, and we tried to compare them with the typical behavior of wrought metal. First of all, we were trying to see some stuff around the microstructure. Of course, the objective of this research was not to identify the full microstructure characteristic of this material, rather to identify the macroscopic response under stress and strain. What came out of some preliminary ACM analysis we did is that this is not the typical wrought metal microstructure. We have seen the alpha acicular martensite structure very evidently, and the titanium 64 is heavily on the alpha microstructure regime rather than the typical wrought metal. Before we start doing any cyclic tests, of course, we did some monotonic tests. We couldn't rely on the tests which have been done in the past by other researchers or either within the university or other universities. So we tested the wrought metal, which was the typical mill annealed wrought metal we obtained from the market, and the SLM produced metals. What we have seen is that both exhibit very similar behavior in terms of the ratio of the ultimate stress to the yield stress ratio. This is important, that's why it is highlighted here, because this ratio shows us the capacity of the, let's say, can predict whether the material can undergo softening, cyclic softening or cyclic hardening. Any value which is below 1.2 means that the material is likely to undergo cyclic softening. In terms of the tests, we did strain control tests, displacement control, and we did two different kind of tests, symmetric tests and asymmetric tests. So the symmetric tests are the typical step loaded tests, which we impose the material to different strain levels under a symmetric, say, load from 1%, 1.5, 1.8 and 2%. And for each strain level, we did 80 cycles. Another set of tests we did was asymmetric tests, where we would like to see some other stuff, which as I'm going to explain. So we did 4 different tests under, let's say, a combination of mean strain and strain amplitude. We kept the strain amplitude constant and we played with the mean strain. For this kind of test, we did 150 cycles, so because we thought that the material had the capacity to undergo, let's say, this level of stressing without a premature failure. In terms of the symmetric tests, again, as I mentioned, we're talking about the step test. So at each strain level, we complete 80 cycles, and then we move to the next level, and so on, until we get either a failure or we get the prescribed number of cycles, in this case 80 cycles. The left graph shows the first cycle out of this sequence for each of the 4 different strain ranges, and the right one shows the last cycle, which is the 8th cycle, both for the wrought metal and the SLM metal. So the wrought is the black line and the SLM is the blue line. If someone would like to see it more evidently, because this is a rather confusing graph, as always, we have seen that in the literature, but it's not ideal, if you'd like to have a better look. So what we did is we decomposed this array of different high hysteresis loops to each one for each strain level. Here we see, for example, at 1% of strain level, the last cycle, and so on. What evidently comes out of this graphs, out of this strain curves, is that the SLM material has less capacity to undergo plastic deformation. In terms of the asymmetric tests, here we have 4 different tests, as I mentioned earlier. Test 1 means that we do a mean strain test at 0.4 and the strain amplitude of 1.2 and so on. So we change the mean strain and we keep constant the strain amplitude. So test 1, here we see the high hysteresis loops for the first cycle and the last cycle. And here the last cycle is the cycle 150. So what we expected to see was actually softening, cyclic softening, and what we see here, actually this is happening for both, for the wrought material and the SLM material. Again, the capacity of the material of the SLM material to undergo plastic deformation, the plastic energy dissipation capacity, as we call it, is let's say heavily impacted by the manufacturing process. Similarly, for test 3 and 4, we see the results which are consistent with test 1 and 2. Another thing which was interesting to examine is how quickly the SLM material and the raw material in that regards is relaxing the stresses under the asymmetric tests. So the stress relaxation is important for fatigue applications, because in practice someone would like to have a material which exhibits fast relaxation, and that way you can achieve better high cycle fatigue. So the left hand side graph shows the wrought material and the right hand side graph shows the SLM material. What we see here, of course, is that first of all someone will observe that there is a higher stress level, so which is identified from these graphs here. So we see the blue line which corresponds to SLM, so we have a larger high hysteresis loop, which is evidently happening here as well. And another thing we observe is how quickly these residual stresses are relaxing for the SLM materials compared to the wrought metal. So this is an indication that, at least with this preliminary results we obtained, is that this material is highly likely to perform much better under high cycle fatigue. Some complementary work trying to simulate these results. So we have been using some models, trying to identify the best possible model which is available here in the literature to simulate these results. So we used one of the models which have been used in the past for other metals, both for simulating symmetric test data, but also the asymmetric test data. And we found that there is a very good agreement in that regards. So this is helpful for simulation purposes without having someone to reinvent or to modify an existing model. So the SLM material seems that it has This is, let's say, accommodating in that regards. In conclusion, as I mentioned, the mean stress relaxation is happening faster for the SLM material. Less plastic work happens on the SLM material, so it means that it is much less ductile, and this goes back to the microstructure. This is something that needs more investigation, but from our investigation so far, it means that we have the potential to utilize this material for LCF applications, for low cycle fatigue applications, if defects are not present. And this is something that we almost always get out of the SLM process. The transient behavior is under cyclic loading can be simulated accurately with the models we have, tested, and this can be very useful for high cycle fatigue calculation, where strain-based methodologies are used. Of course, we have more work to do, and we're currently doing this work at RMIT University and the University of Limerick as well, in conjunction with the Defence Science and Technology Organization in Australia. First of all, we need to look deeper in the microstructure. Secondly, anisotropy. Not anisotropy from the point of view of monotonic loadings, but also from the point of view of cyclic loadings. So we have already under review, it's the same paper in practice, which reports these two findings. Unfortunately, I'm not able to disclose this at this point. There may be a reviewer here. Okay, so thank you, and if you have any questions.